In this video, we're going to take a look at gas laws, Boyle's law and Charles' law. So Boyle's law relates pressure with volume. As the pressure changes, we know that the volume also will change. There is a relationship between pressure and volume. They are inversely related. So for any given gas that's at a constant temperature, volume and gas, again, are inversely proportional. As the pressure changes, the volume will change the opposite direction. By doubling pressure, it's going to cut volume in half. If the volume were to triple, the pressure would be cut by a third. So we see that in this mathematical representation, P1 V1 equals P2 V2. So the product of the pressure and volume at any set of conditions is equal to the product of any other pressure and volume at a different set of conditions. So let's take a look at what one of these problems would look like. If we have a balloon and it contains 50 liters of helium gas at 105 kPa, and we release it and it rises up in altitude and the pressure is only 30 kPa, the temperature again is going to remain constant. What is the volume of the balloon? So the only things that are changing here are our pressure and our volume. So let's list out what we know and what we don't know. We know that we have a volume of 50 liters. And again, that we do know that there are two different pressures here, so there are going to be two different sets of conditions. So we're going to call that V1. It has an initial volume of 50 liters. And that initial volume is 50 liters when the pressure is 105 kPa. So again, any set of pressure and volume together doesn't matter if it's the before or the after. If you call those V1, V2 and P2, that'd be okay. But usually just as the problem reads, you want to list them as the initial versus the final, the first versus the second. But if you had listed them two and then the other one's one, that works out just fine too. So then when it's released, the pressure now reduces down to only 30 kPa. So that's our second pressure. And then lastly, what is the volume of the balloon? That's what we're trying to solve for. So again, we're going to use Boyle's law. P1 V1 equals P2 V2. Then we're going to take that equation and we're going to solve it for our unknown. Rather than try and plug numbers in and then manipulate this equation with all the numbers, and then it gets a little cumbersome and much more likely to make little silly mistakes, we're going to move the letters around and solve the equation so it says V2 equals. So to isolate V2, we're going to divide both sides by P2. Then P2 reduces out, and it leaves us now with the equation V2 equals P1 V1 over P2. Now we can plug in our variables, and I have 105 kPa times 50 liters divided by 30 kPa is now going to equal V2. Again, kPa divided by kPa will reduce out. It'll leave us with a unit of liters, which is good because volume is measured in liters. And we find that we now have a new volume of 175 liters. This makes sense because, again, pressure and volume are inversely related. So if the pressure is getting reduced, our balloon is going to expand and take up more space. So the volume should increase. And an increase from 50 up to 175 would be about 3 times, which 105 to 30 is about 1/3. So I know that's roughly a good answer. So the next relationship we're going to look at is volume and temperature. This is related in Charles' law. So now keeping pressure and the amount of gas constant, and now just volume and temperature are changing, how do those two things relate? Well, we know when temperature increases, volume also increases. There's a direct relationship for a gas between temperature and volume. Again, as long as the amount of gas and the pressure which it's under stays constant, we can see that direct relationship between these two different variables. And that direct relationship is going to be represented by this equation of V1 over T1 equals V2 over T2. So when they were inversely related, like pressure and volume, we multiply them together. Since they're directly related, we're going to divide. So let's take a look at a couple different examples, because this one gets a little bit trickier where volume and temperature, one is a numerator, one's a denominator, so the process is a little different for both. So this first one we're going to look at is a balloon that is filled up with helium, and it's at a temperature of 28 degrees Celsius, and the volume is 2.5 liters. Then we take it outside, and the temperature is only -5 degrees Celsius. What is the new volume of the balloon? So the first one we're going to look at is going to relate volume and temperature. I'm going to solve for a volume. So we have a balloon that's filled with helium, and we filled it up inside where the temperature is 28 degrees Celsius. And that temperature had a volume of 2.5 liters. However, then we go outside, it's much cooler out, and it's only -5 degrees Celsius out. So what is the volume of the balloon? So let's take a look at our knowns and our unknowns again, kind of list them out as they appear and get an idea of what's happening. We do see there are two different temperatures here, so we do have two different sets of conditions. So we're going to use those subscripts once again, 1 and 2, to show those different sets of conditions. So first we know that we have a temperature of 28 degrees Celsius. And again, we start off inside, so we'll give that a subscript of 1. So T1 is 28 degrees Celsius. And when it's 28 degrees Celsius, we know the volume is 2.5, so that is V1. Again, those ones got to make sure they match up. If you'd called those T2 and V2, that would have worked okay. But again, if you kind of give them as the problem reads, it makes it a little bit easier to keep them together. So then we walk outside, so our second set of conditions is now T2 is -5 degrees Celsius. And then lastly, what is the volume of the balloon? That's our unknown. So we have two temperatures, two volumes, so now we're going to use Charles' law. V1 over T1 equals V2 over T2. However, we're not quite ready to just start solving away yet because we have these degrees Celsius. Now, if I were to plug in that 28 and that -5, we'd have to end up with a volume that is a negative volume, which makes no sense. So the only way this equation works is when we use temperature on the Kelvin scale. So we got to convert those temperatures to Kelvin. So to get from Celsius to Kelvin, we're going to add 273. So 28 plus 273, we find T1 to be 301 Kelvin. And the -5 plus 273, we find T2 to be 268 Kelvin. And now, let's take our equation. We'll manipulate the equation to solve for V2. So this one's pretty simple. Again, one step of algebra here. Move T2 to the other side to get V2 all by itself. So you can multiply both sides by T2. T2 again reduces out, leaving us now with the new equation. V2 equals V1 T2 over T1. And now I can take my variables, I can plug in those values and solve for V2. So 2.5 liters times 268 Kelvin divided by 301 Kelvin. Again, our Kelvin's going to reduce out, and we find we have a new volume of 2.23 liters. Now we started at 2.5 and it went down to 2.23, so that makes sense because we know volume and temperature are directly related. So as it gets cooler outside, as we change the temperature of our balloon to a lower temperature, it should get smaller. So this next example is a little bit more tricky because we're going to solve for T2. So in a piston that has a volume of 250 milliliters when it's depressed, has a temperature of 450 Kelvin. Then the piston is raised and the volume expands to 1,250 milliliters. What is the new temperature? So let's list out what we know and what we don't know. Again, we'll go through the problem kind of as it reads, and that'll help us fill in the blanks of what we have. We have two sets of volumes, so again, we're going to have, therefore, two different sets of conditions. We are going to need the subscripts here again. So we do know that the volume, to start, the initial volume is 250 milliliters. V1 is 250 milliliters. And then at that volume, the temperature is 450 Kelvin. So temperature, T1, is 450. Luckily, that's already in Kelvin, so we're not going to have to change that to Kelvin because it's already there. But then the volume expands to 1,250 milliliters. So V2 is 1,250 milliliters. And then solve for what is the temperature at that volume. So T2. So let's take a look at our equation. Our equation, again, is going to be Charles' law, relating volume and temperature. Again, the amount of gas and the pressure are going to be constant. But now I get this problem of T2 is in the denominator. So if I were to try to isolate T2 and just move V2 to the other side, I'd divide both sides by V2, and I'd be left with 1 over T2, or the reciprocal of T2, and that doesn't do me any good, or the inverse of T2. You wouldn't solve for 1 over X. In math class, you're not going to solve for 1 over T2 with this problem. So we need to get T2 to the numerator, and the easiest way to do that is to just take an inverse of the entire equation, and now we're going to flip the entire equation both sides, and we now get T1 over V1 equals T2 over V2. And now it's much more simple to isolate T2. If I multiply both sides by V2, V2 reduces out, leaving me now with an equation T2 equals V2 times T1 over V1. And now I can just plug in my variables. So I know that V2 is at 1250 milliliters, T1 is 450 Kelvin, and V1 is 250 milliliters. Milliliters divided by milliliters, that's going to reduce out. And then I find now my new temperature is 2,250 Kelvin. So again, that makes sense because we know volume and temperature are directly related. So if the volume is expanding, well, it's expanding because the temperature is also expanding. As the temperature increases, the volume is going to increase. They do change at the same rate. So that 2,250 Kelvin is a good possible answer.